Hey, I'm Mrs.Compile and today we will explore load balancers. How websites survive Black Friday, the World Cup final, and general internet chaos. No boring lectures, just how it actually works. Let's go! Last episode, we opened up what a server actually is. A computer optimized to respond to requests, handling thousands of connections, using threads or event loops, static files or dynamic content, living in data centers with redundant cooling, and even redundant everything. If you missed it, link in description. Worth watching before this one. Because today we are asking, what happens when one server isn't enough? Black Friday, a major retailer, midnight. The deal goes live. Millions of people hit the website exactly the same time. The server is handling it. Just about. CPU at 80%. Memory climbing. Then it hits 95%. And then 100%. And then the site goes down. Not slowly, all at once. People refreshing. Twitter going wild. Customer service overwhelmed. The company losing roughly £50,000 per minute. One server cannot handle the entire internet. This is not a software problem. It's a physical problem. It's like having one cashier at supermarket on Christmas Eve. Doesn't matter how good they are at scanning. Doesn't matter how motivated they are. The queue is longer than the car park. The system is the problem, not the person in it. The solution isn't a faster server, it's more servers. And something in front of them that decides who handles what. That something is called a load balancer. A load balancer sits between the users and the servers. Every request hits the load balancer first. It decides which server handles it. The request goes to that server. The response comes back through the load balancer. The user sees the result. From the user's perspective, nothing. They type a URL. The page loads. They have no idea there are 4 servers behind the scenes. It's like a restaurant kitchen. You sit down, you order. Food arrives. You don't know if one chef made your starter and a different chef made your main. You don't know how many people are working back there. You just know the food arrived. On time. Correct. Hot. The load balancer's core job is simple. Spread the work. If server 1 is busy, send the next request to server 2. If server 3 goes down, stop sending traffic there entirely. Keep everything running smoothly. It is genuinely a traffic controller for the internet. But how does the load balancer decide which server gets which request? There are several strategies. Let's start with the simplest. Round robin. Request 1 goes to server A. Request 2 to server B. Request 3 to server C. Then back to server A, cycling through one by one. Fair, simple, no favorites. Very democratic. The load balancer doesn't think. It just cycles. Perfect when all your servers are the same spec and doing similar work. Least connections is smarter. The load balancer checks which server currently has the fewest connections and sends the next request there. Like choosing the shortest queue at the supermarket. Except it actually works. Unlike my personal experience, where I always pick the queue that turns out to have a price check. Poor me. Second, IP hash is interesting. The load balancer takes your IP address, runs it through a hashing algorithm, and uses the result to decide which server you should go to. The key thing, the same IP always produces the same result. So, you always hit the same server. Why does this matter? Session persistence. If the server is keeping status about who you are, your shopping cart, your session token, your in-progress form, you need to consistently reach the same server. IP hash guarantees that. And then there is a weighted distribution. Not all servers are equal. You might have a brand new powerful machine and an old one running on prayers and mild optimism. Give the new one 70% of the traffic. Give the old one 30%. Play to your strengths. Don't waste your best server's capacity. Weighted strategies are also useful during developments. You can greatly shift traffic from the old version to the new one. Send 10% to the new server. Watch it carefully. Then 25%, then 50%, and then 100%. A controlled rollout. If the new version breaks, you have only affected 10% of users. Roll it back. Fix it. Try again. Here's where load balancers go from useful to essential. They don't just distribute traffic, they actively monitor server health. Every few seconds, the load balancer sends a ping to each server. A health check. Are you alive? Can you respond? It might check the root URL. A 200 response means the server is healthy. It might check a dedicated health endpoint, /health, which returns server status. It's like a teacher doing the register, going through the list. Server 1, present. Server 2, present. Server 3, nothing. Server 3, still nothing. Make it absent. Move on. Send the next request elsewhere. The load balancers mark server 3 as down. Immediately stop sending traffic there. No human intervention. No alerts that anyone needs to act on right now. The requests that would have gone to server 3 now go to server 1, 2, and 4 instead. The users don't notice, not even a slight slowdown. If it's handled correctly, the broken server gets fixed, come back online, passes the health check, and the load balancer welcomes it back. Traffic resumes. This is why Netflix can have servers crash and you never know about it. Why Google can do maintenance at 3 a.m. and you never see a downtime page. Load balancers are slightly keeping the internet running every second of every day. Load balancers come in two forms. One is hardware load balancers, and they are dedicated physical devices. They live in data centers. They are expensive. We are talking tens of thousands, but they are powerful and battle tested. Banks, financial institutions, critical infrastructure, they use hardware because when the cost of downtime is larger than the cost of the hardware, you buy the hardware. It's software load balancers, and they are programs running on regular servers. Nginx and HAProxy are the most widely deployed. They are open source, free, and extraordinarily capable. A one-line Nginx config can turn any server into load balancer. Most of the internet runs behind one of these two. Second, cloud providers offer managed load balancers as a service. AWS Elastic Load Balancer, Google Cloud Load Balancing, Azure Load Balancer. You configure it through a dashboard. Point it at your servers. Set your health check. Done. No hardware, no maintenance. Pay by the hours. The cloud actually earns its name here. A load balancer sits between user and servers. It distributes traffic using strategies, round robin, least connections, IP hash, weighted. It monitors server health every few seconds and automatically reroutes around failures. It comes in hardware form for critical infrastructure and software form like Nginx, HAProxy for most of the internet, and cloud providers offer it as a managed service. Load balancers are the reason you can use Instagram during halftime of the World Cup final without it going down. Well, usually 6 episodes in, DNS finds the address. HTTP makes the request. TCP/IP delivers the data. HTTPS keeps it secure. Servers handle the response. And load balancers make sure one server crashing doesn't take down everything. Starting to see how the internet actually holds together? Next episode, speed. Because even with load balancers and multiple servers, hitting a server for every single request wastes time and compute. What if the server remembered the last time you asked? What if it could serve the same answer without doing the work again? It's caching, the internet's memory, and it's everywhere. And that's load balancer sorted. Smash the like button if this helped. Share it with someone who still wondered why website crash on Black Friday. Subscribe so you don't miss the caching episode. It's a good one. I am Mrs.Compile and I'll see you in the next one.